Look at Atlantis the Royal. To the naked eye, it appears to be a stack of massive, independent blocks, hovering dangerously over the edge of Palm Jumeirah. It looks like it could break in half at any moment. But that massive visual separation is a dangerous illusion. This entire 400-meter megastructure was built entirely without a single conventional expansion joint, and that is a high-stakes bet against the laws of physics. In an extreme coastal desert, where intense thermal energy and heavy ocean winds constantly force enormous concrete masses to warp, bend, and twist, buildings desperately need room to move. By all conventional logic, removing the physical gaps designed to absorb that movement should violently tear the building's connections apart and shatter its glass skin. Yet, engineers deliberately removed the one safety mechanism designed to save it. So, what happens when a massive structural giant is constantly trying to rip itself apart, but is forced to fight its own geometry to survive? To understand why removing these joints changes everything, you have to understand why they are normally there. An expansion joint is essentially a planned and controlled gap that physically separates one section of a building from another. If you have two massive blocks of concrete and steel, they will naturally expand outward when heated by the sun and contract inward when cooled at night. If there is a gap between them, that relative movement has somewhere obvious to occur. The two blocks can slightly shift or expand independently without crashing into each other. Without that simple physical separation, relative deformation must be handled differently. If the structure remains entirely continuous, those two masses will fight each other as they try to move. The strange thing about an engineering expansion joint is that deliberately breaking the physical continuity of a massive structure is exactly what protects the integrity of the larger system. It is a physical gap that functions perfectly as a structural shield against extreme forces. Atlantis, the Royal visually appears to be completely divided already, with massive voids letting the sky show through. So how connected is it really? The exterior masses of the resort tell a convincing story of complete physical separation. You see wide-open voids and floating sky courts, and distinct vertical sections that look detached from their neighbors. But if you strip away the glass and look directly at the heavy steel and concrete skeleton, that narrative disappears entirely. Hidden inside the floor systems and the thick concrete core walls and the structural framing is a massive network of continuity. The above-podium superstructure stretches for more than 400 meters along the coastline. Across that massive horizontal length, the building is rigidly tied together. The architecture keeps pulling these building masses apart visually. The engineering keeps tying them back together. The forces acting on one end of this 400-meter continuous system cannot simply be ignored by the other end. Because they do not have joints to isolate their behavior, the individual towers cannot act like solo performers. They are forced into a single continuous structural system, and the most dramatic physical connection between those masses is not hidden inside a concrete slab. It hangs right out in the open sky between the towers. The main sky bridge spans more than 105 meters between two primary tower structures. This is not just a decorative corridor or a high-altitude luxury terrace. It is a massive structural connection, weighing approximately 1,350 tons. When you physically link two huge structural masses with something that heavy and rigid, you create a highly complex engineering relationship. If the tower on the left wants to move slightly in one direction, and the tower on the right wants to move in another, they can no longer do so in isolation. The sky bridge creates a direct and unavoidable structural path between them. It acts like a massive steel handcuff holding two swaying concrete giants tightly together. The bridge does not merely connect hotel spaces and swimming pools. It helps structurally connect the physical behavior of major building masses. The movement of one side now has a structural path to travel directly into the other side. And the first major force trying to alter this connected geometry is something Dubai provides with extreme intensity every single day: temperature. When the morning sun hits the eastern facade of this continuous system, the structural materials begin to absorb massive thermal energy. Metals and concrete naturally want to expand as they get hotter. But because of the unusual curved geometry of Atlantis, the Royal temperature-driven deformation is not only a simple question of the building trying to become longer or shorter, it also fundamentally affects curvature. Different sides of the building heat up at different rates depending on the time of day and the angle of the sun. This uneven heating causes different sections to want to bend or twist or lengthen at slightly different speeds. A straight steel beam getting slightly longer is easy to imagine. A multi-tower continuous structure trying to alter both its total length and its curvature simultaneously is a very different physical problem. That deformation creates immense physical demands deep inside the concrete floor diaphragms and the steel skybridge elements and the connected structural joints. The project's structural engineers at WSP clearly understood this serious environmental threat, and they actively investigated the most obvious escape route. When dealing with a structure spanning more than 400 meters under intense thermal variation, standard engineering practice points toward separation. The project design team actively investigated several different traditional jointing strategies. They conducted extensive movement control studies to see how the building would behave if it were chopped into independent sections. They analyzed what it would take to insert conventional expansion joints that would allow the heat-driven length and curvature changes to happen harmlessly. This is the standard engineering playbook for long horizontal megastructures across the Middle East. You find the points of highest physical stress, and you break the continuity, and you let the building move. Obviously, giving the building room to expand, without pulling at its own internal connections, must have been the final solution they chose. It was not. After extensive study, the engineering team made a counterintuitive decision. The continuous structural solution, without conventional expansion joints, was selected for the entire tower superstructure. They deliberately rejected the physical gaps that would have easily absorbed the thermal expansion and structural shifts. This is the exact moment Zero stops looking like something that was accidentally forgotten on the engineering blueprints. It becomes a highly deliberate structural commitment. They chose to tie the entire upper framework together into one continuous system, knowing exactly how much thermal energy the Dubai environment would pump into it. But refusing to provide an expansion joint does not magically cancel out the basic laws of physics. A joint would have given all of that intense thermal movement somewhere obvious and harmless to occur. Atlantis the Royal chose total structural continuity instead. So if the building cannot easily separate to relieve the environmental pressure, where does all of that movement actually go? If a building cannot naturally separate to relieve pressure, the movement does not simply disappear. It transforms into something much more dangerous. When a massive concrete structure wants to expand, but is forcefully restrained by its own continuous design, that restrained deformation becomes internal force. Engineers call these forces continuity stresses. Instead of avoiding the physical stress through a gap, the building must absorb it entirely. The strain travels deep through the concrete floor diaphragms. It transfers heavily into the rigid connections. It creates immense physical demands on the skybridge and the connected structural joints between the towers. The core engineering issue for WSP on this project was that continuity stresses from multiple sources had to be understood and accommodated. This is a complete reversal of conventional building design. A traditional strategy partly manages movement through deliberate separation. The Atlantis strategy manages the consequences of movement through absolute continuity. And even if Dubai's intense temperature suddenly became perfectly constant, the physical geometry of this structure would still continue changing. Even if you remove every gust of wind and every swing in temperature, a concrete megastructure is still constantly in motion. When massive gravity loads are applied over long periods of time, the vertical columns and core walls undergo elastic shortening. But concrete also experiences long-term creep and shrinkage. The material itself slowly compresses and loses volume as moisture slowly leaves the matrix and internal stresses settle over many years. If temperature means the external environment is the clock creep, and shrinkage meantime itself is the clock. Because the Atlantis structure is continuous, these volumetric changes do not happen evenly. Different towers and different core walls compress at slightly different rates, based on their physical loads and their individual stiffness. Engineering studies for the project had to account for this long-term axial deformation and calculate precise compensation for differential effects. Tomorrow's building is simply not geometrically identical to today's building, even under perfectly calm environmental conditions. There was also a specific period when managing all of this movement was much harder than it is inside the finished luxury resort. When you look at Atlantis the Royal today, it is a sealed and climate-controlled environment. But long before the luxury interiors were installed, Dubai got the very first move. During construction, the unfinished concrete skeleton and bare steel were exposed to the elements. Without the protective building envelope and the finished HVAC systems, the structure experienced much more direct ambient temperature variation. The intense sun beat down on open floors and exposed structural joints day after day. The system had to handle this severe daily thermal cycle while it was still incomplete. Its stiffness was constantly changing as massive amounts of new concrete were poured. The gravity loads were increasing every single day as the towers climbed higher. And the future long-term deformation from creep and shrinkage was only just beginning its timeline. The unfinished structure had to survive its most exposed state, while its ultimate load paths were still being formed. So heat is already acting on the system. Time is already acting on the materials. The structure is entirely continuous. Now introduce one more environmental force. Ocean wind pushing heavily against a massive surface area forces a structure to bend. When wind hits a conventional independent tower, that single tower simply sways in response. But when wind attacks a connected multi-tower system, it pushes different parts of the exact same continuous structure differently. The architecture of Atlantis does provide one major physical advantage here. The large visual openings and voids actually help coastal wind pass straight through parts of the building, reducing some of the aerodynamic impact. This is a highly useful design feature, but that does not eliminate the engineering problem. The long floor plates and multiple concrete cores and massive sky bridges still produce a complicated global structural response. The project wind engineers reportedly conducted approximately twice the usual number of wind tunnel studies for a building of comparable height. Every tall structure experiences heavy wind. But the unique problem here is that the response of one connected portion cannot be understood as though the neighboring towers simply do not exist. Wind effects can be reduced, but they cannot be made to disappear entirely. So where do all these remaining forces actually travel? The missing expansion joints were not replaced by one secret miracle component. There is no single enormous damper or hidden beam that absorbs all the continuity stress. Instead, the global structural system itself had to become the primary movement management strategy. When wind or thermal expansion pushes hard on one tower, the force travels through a highly specific load path. It moves straight down the massive concrete core. It transfers aggressively across the rigid floor diaphragm. It travels directly through the heavy steel sky bridge. And it pushes directly into the neighboring structural system for global redistribution. The strict continuity that restrains the building is the exact same mechanism used to redistribute the internal forces. The engineers deliberately tied the masses together so the entire global structure could share the immense physical loads. We know what forces try to deform the building, and we know they are transferred throughout the entire continuous system. But the engineering models describe a fully completed building. The construction teams had to start by building something incomplete. How do you build a continuous geometry when you already know that geometry is guaranteed to change later? The answer involves a process called construction stage compensation. Engineers do not simply build the structure exactly where they want it to end up. They have to calculate where the structure will be during construction, predict the expected deformation, and then target a future position. The engineering work considered specific compensation values to heavily reduce the differential axial deformation effects across the connected towers. Sometimes building a massive structure accurately does not mean placing every concrete column and floor slab exactly where you ultimately expect it to remain. It means explicitly building for a future shape that time and gravity will eventually pull into the correct permanent alignment. This requires immense physical precision to ensure the continuous structure settles safely. But what happens if this continuous system fails to handle the movement properly? If engineers had misunderstood these forces, what would physically begin failing first? What would incompatible movement look like before a cinematic failure occurred? If the structural system could not handle the immense continuity stresses, the building would not immediately rip down the middle. Tearing apart would begin at a much smaller and highly localized scale. When restrained deformation creates overwhelming internal force, the very first casualty is usually a physical connection. Incompatible movement triggers severe local deformation, which concentrates heavy stress at critical joints. For the massive sky bridge connecting the towers, engineers evaluated deformation partly through measuring slopes and local gradients. If those structural gradients exceeded acceptable limits, the connections would experience severe physical distress. That distress could lead to concrete cracking or the dangerous yielding of critical steel nodes. A failure at a local connection fundamentally changes the structural stiffness of that specific area. When stiffness changes, the massive forces of wind and gravity and temperature are suddenly forced to find a new load path. That rapid load redistribution is exactly what could eventually trigger much broader and potentially catastrophic structural consequences. A structure does not need to split visibly into two giant pieces before continuity becomes a terrifying engineering problem. And some of the earliest visible evidence of this movement might not appear in the massive concrete cores at all. It might appear directly in the exterior skin that people actually look at. What does the architecture itself have to tolerate when the massive global structure moves? This physical reality introduces a completely different stakeholder into the engineering equation: the facade engineer. Atlantis the Royal is tightly wrapped in vast expanses of heavy glass and architectural cladding and complex balcony edges. When the continuous structural skeleton bends or twists under heavy thermal and wind loads, the exterior skin is forced to go along for the ride. Structural movement must remain compatible with building envelope serviceability and tight architectural tolerances. Project literature from WSP describes close coordination between the structural and facade engineering teams. This was especially critical around the highly exposed luxury terraces and the complex wind-facing exterior surfaces. If the continuity stresses forced the steel frame to distort beyond what the facade could physically absorb, the glass would shatter and the exterior cladding would buckle. The human-scale details become a highly visible witness to the invisible structural forces traveling through the system. So if a simple physical gap is not protecting the glass and the connections what actually makes this continuous strategy workable, what ultimately replaces the simple protective role that a conventional expansion joint would have played? There is no single miracle component hidden deep inside the concrete to save the building. The ultimate solution was extreme system-level structural coordination. Intense temperature variation and long-term concrete shrinkage and heavy gravity and coastal wind and complex construction sequencing all had to be combined. Engineers ran a complex global structural analysis to understand exactly how all of those natural forces interacted simultaneously. That deep analysis dictated a meticulously designed structural load path and highly specific deformation compensation during construction. Finally, everything was verified through serviceability checks and intense structural facade coordination. The conventional engineering philosophy treats structural movement as a physical threat that must be separated. The Atlantis philosophy treats structural movement as an absolute physical certainty. Engineers chose to predict it and redistribute its consequences and ultimately accommodate it through pure structural continuity. Which brings us directly back to the most alarming question of the entire investigation. Could Atlantis the Royal actually tear itself apart? To answer that, you have to distinguish the catastrophic cinematic image from the strict engineering pathway. If incompatible movement demands had not been predicted, the restrained deformation would have easily generated overwhelming continuity stresses throughout the connected towers. Those unchecked physical stresses would immediately initiate severe local deformation and dangerous concrete cracking and heavy connection distress. That localized structural failure would rapidly alter the stiffness of the entire system, forcing massive physical loads to suddenly redistribute. Only at the absolute far end of that progressive failure pathway do you reach the catastrophic structural consequences implied by tearing apart. The public engineering evidence does not establish that Atlantis the Royal is currently undergoing this kind of terrifying structural failure. Instead, it explicitly explains the exact structural failure pathway that designers actively had to prevent when they deliberately selected continuity over conventional separation. Tear apart is not where the engineering problem begins. It is the absolute worst-case scenario at the far end of a complex chain that must be interrupted much earlier, which fundamentally changes how we understand the very first anomaly we noticed: zero expansion joints. At the beginning of this investigation, zero sounded like a dangerous missing piece of fundamental structural protection. At the end, it represents a deliberate and complex engineering philosophy. The resort creates a brilliant visual illusion. What the human eye sees is a series of separate blocks and open courts floating independently over Palm Jumeirah. What the structural skeleton experiences is constant physical interaction and shared forces and massive load redistribution. Those seemingly separate massive concrete blocks have to remain aware of what the others are doing at all times. This documentary is an educational engineering analysis based strictly on publicly available design literature. Could Tear Apart examines a theoretical structural failure pathway. It does not claim Atlantis the Royal is currently approaching catastrophic structural failure. Structural behavior should not be inferred beyond cited sources. So I want to ask you a specific question. Would you trust a giant building more if its sections could move independently, or if engineers deliberately tied the entire system together? Let me know down below and subscribe for more documentaries.